Okay, second. Hmm. Okay, perfect. So then we're gonna basically, yeah. So we did till here. If you guys have any questions about any of these graphs, please let me know. All right. So we're going to go forward and look at this question where it says two isolated metal spheres M and N. Each of radius R are situated in vacuum, they center distance and blah blah blah. If you notice, both of them are positively charged, and then they say uh, each sphere has a charge plus q, and p lies like this distance. So show the variation of electric potential at a point for the values like this, right? So obviously,
So are you sharing the screen?
yes, you can't see.
No.
Is it same for everybody?
No, sir, I can't see it either.
Sir, I can see.
Okay, I'm
I
gonna
can't see it though.
I'm gonna stop and then I'm gonna share again. No worries. Okay, can you guys see now?
No, sir, let me leave and join again.
Wait, that's
Sir, I can see.
okay. Juveria?
Yes, I can see it.
Okay. All right, let him be back.
Yes, sir, now I can see.
Okay. All right. So, where was I? Yeah. So in the question, it says that you need to find the variation. So the variation with distance y of the electric potential P for the values of y from y equals to d to y equals to d. Okay. So that's basically this is this distance, right? So we're going to start from here. So we're going to reach r. At r we will have maximum potential, obviously, and it's going to be positive. So we're going to go up, we're going to point here, okay? And then because we know that potential graph for this one should be like this, and for this one it should be like this, like potential should increase. And basically this is like at this point, when you reach this point, this should be like d minus r. That's what they've written here. So so it's going to be up again like this, and it will never touch zero. So exactly at the middle, which is basically from here till here, it's like half, one, two, and half. So I think the middle would be somewhere like here, I believe. You just is it the middle? I don't know if it's the middle. This 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 should be the middle, right? So take any point and then make a smooth curve like this. It should not touch zero at any point because potential will not be zero. So remember that. Okay, just like we have done previously, so it's the same. Okay. All right, please draw this and let me know if you have a question here.
So don't we need to show a straight line inside this way?
Yeah, we should, but we haven't gone through that yet. That's fine.
Okay.
But it should be, you're talking about this line, right?
Yeah.
Yeah, we should, but we haven't covered that, so that's fine. But it should be straight. That's true. All right. Anything else? Anything you would like to ask from this? Please let me know. Just remember that what Gatika is saying, she's saying within any sphere, the potential is constant, which means that till you reach the surface of the sphere, whether you're reaching from here or here, the potential value will stay constant like that. Is it clear? All right. Then in the next one, it says these are the graphs. It says what is the electric potential at a point. Obviously, it is the work done. You can write work done per unit charge. So you should write that. In bringing this charge from infinity to a point. So if you write it, you get 2 marks. It's very simple like that. And then you see this is 2 charges are separated in a vacuum, and they've also shown the potential lines, right? So for potential of A and potential of B, and they say that state and explain whether the charges are of same or opposite sign. If you look at the thing, you might understand that both of them, basically the positive potential decreases, and then on the other side the positive potential increases. So it means both are positive charges. Do you guys understand this? Okay. So then for 2 marks we're gonna write that the potential of both charges is positive, which means they have the same sign. All right, everyone. All right. If you still have any confusion, please let me know. Okay. Then it says by reference state how the combined electric field due to both charges may be determined. Yeah. So electric field strength. Combined electric field due to both charges might be like, how do we determine that, right? So it's very easy. What you do, you have to add up like each individual point, like you add this, and then obviously when you add these 2 lines, you're going to get a potential graph like this, right? Which is the net graph. That's what they're talking about. So we can say that by adding individual points on the graph. All right, so we can write that, and then without any calculation, estimate the distance x which the combined electric potential of 2 charges is minimum. Obviously it's going to be where they're right here, they're meeting right here, obviously, and that would be, I think, if you go down, what that might be, if this is 13.2, 13.4, 13.3, so we're gonna write 13.3, just like that, right? Is it clear? Then it says the point P is a distance 10 from A, and alpha particle has kinetic energy K. Oh, okay. This question, I'm going to start it, and this is for your homework when we do the, kinetic energy thing later. All right, so we're going to come back either later or we're going to do it. But can we still do it? I don't know. We should do it or we should not do it. I think we can do it. We can still do it. We don't need that kind of. Anyway, so what we need to do is at x equals to 10, we're going to go there. And if you notice at x equals to 10, the combined potential, like this one is like I think this is 0.1, so 0.2, 0.14. You guys agree?
0.14.
Yes. And at this point, this is going to be almost, this is 0.3, so 0.28, right?
0.29.
29?
8.
29, yeah, 29. Okay. Can you add them up? What you get? What would be the potential? 0.29 plus 0.14.
0.43.
0.43 volts. So this is the net potential because of both fields here. So if there was an alpha particle, so we got the potential value. All right. And then alpha particle basically is of 4 and 2, which means this is its mass, which is 4u, and this is its charge 2e. So we know that we need to find the minimum value of kinetic energy. So we need to do that work to basically, so we need to provide this kinetic energy so it can do that kind of work. And work done is potential times charge. That's the definition of electric potential. So then we're going to write 0.43. And the charge is 2 times 1.6 times 10 raised to minus 19, because 1e is equal to 1.6 times 10 raised to minus 19. All right, what you get?
1.38 times 10 raised to minus 19.
1.38 1.38 times 10 raised to minus 19 joules would be the answer then. Okay, everyone, any questions? Oh, crap. The next then. So the next is basically the null point, and we got to learn how to find it. So it's pretty easy. All you need to understand is that the null point has a couple of features that we're going to talk about. First of all, you should understand that at null point, the force of the charge, one charge, and the force of other charge got to be equal. So which means if I'm talking about force due to Q1 and force due to Q2, they should be equal and opposite. And same goes for the electric field strength. So electric field strength at this point, because of Q1, should be equal to electric field strength because of Q2. And that's how, when you add them up, because they're basically vector quantities, they cancel them out, right? Is it clear? All right, now, so keeping that in mind, then we're gonna look at some of the features of a null point. Okay. So when you basically talk about the null point in general, so all right, so you guys should understand this very important fact that at this point we are gonna say net force is equal to 0. Net, sorry, I'm writing gravitation. Electric field strength is also 0. All right, so then here I just want to tell you that at this null point where we're talking about this, you never write that the potential, net potential, is never 0. It is the minimum here, but obviously it will never be 0, so you just need to remember that. Okay, now okay, so then we are gonna talk about how we can determine null point. For example, there's a step, like for example, when you find the null point where the force is 0, so you can write it as like k q1 q2 over r1 square should be equal to k q1 q2 over r2 square. So they're basically the same, right? Or you can write it as k q1 over r square equals to r1 square and k q2 square over r2 square, like that. So either you use electric field or force, that would be the same thing. Okay, anyway, this is magnitude wise, by the way. Anyway, then we are going to talk about the next step. So let's suppose there's some charge that moves from some point to null point. The next logical step is that you are going to find the potential at the initial value. So you're going to find the potential at the midpoint, which is right here, and then you're going to find the potential at the null point, which is here, right? So when you find the midpoint and the null point, you're gonna find the change in potential. Change in potential would be like higher minus lower. So what you do is you always do larger value minus the smaller value. The reason why you want to do this is because this is a scalar quantity, and scalar quantities we don't do final minus initial, we do larger minus smaller, like that. And then finally we would use work done equals to change in potential times the charge of this particular charge, whatever that is, to find the work done in moving a particular point from one point to another. Is it clear? So what I've done is I've laid out a map. So in 5 steps, if such question comes, you can always find the right answer. So again, I'm just repeating. At the null point, net electric force is 0, net electric field is 0. When you are looking at a charge that moves from one point to another, you're going to find the potential at that point, potential at the other point, and then find the change of the potential, and whatever that is, you're going to multiply it with the charge of that particle that is moving, and obviously you're going to get the work done in doing so. All right, is it clear, everyone? Any questions? Please let me know. Okay, so yes, now Fahar, Gatika, Mokshit, Munib, Suman, Ahmed Squares, Aman, Anusha. Everybody understands this? All right. So now let's move to a very similar question. So in this one, it says there's an alpha particle and there's a proton, and then there's a point P. I don't know what that is. It just says state the Coulomb's law. The first thing you should understand that force is directly proportional to the product of charge, and it is inversely proportional to the square of their distances from center to center. So you can write it like that. So you can write it in words. And then it says alpha particle proton may be considered to be point charges. Calculate the electric force between alpha particle and the proton. So what you're going to do is, first of all, you should understand alpha particle is 4-2, which means it has a charge of 2e, and proton is 1-1, which means it has a charge of 1e. So the force is going to be k, like k q over r square, and I'm going to write 8.99 times 10 raised to 9. That is the value of k. The charge on an alpha particle would be 2 times 1.6 times 10 raised to minus 19. E is 1.6, and then times 1.6 times 10 raised to minus 19. And then we're going to divide this by the distance between them. Distance between them is 20 micrometers, which is 20 times 10 raised to minus 6. And you got to whole square it. So what you get? Go on, please.
1.15 times 10 raised to minus 18.
Minus 18 newtons. Okay, fine. Then it says
1.2 to the power of negative 18.
1.2. Okay, that's fine. You
See.
can write this, or you can write 1.2. Both are correct answers. Do not go beyond this or less than this. Anyway, so then it says define electric field strength. And obviously we're going to write the electric field strength is the force per unit charge per unit positive charge at a point within the field. Okay, writing positive charge is a convention, and it is very important, and it does hold marks. So if you don't, you probably might lose, and this is the reason why they will give you this as 2 mark definition. Okay. Anyway, then going here, so they've given you the graph of electric field strength, and they say explain why the two separate electric fields have opposite signs. So you should understand that although they're positive charges, but the reason why they have opposite signs is because electric field strength, all right, electric field strength, like you see, it's a graph of electric field strength, and it's a vector quantity. So electric field strength is a vector, hence the field is in the opposite directions. That's why they would have different signs. And then it says sketch the variation of X combined electric field, and it's very easy. What you're going to do is you just need to find the sweet spot where both of them equal, and that would be here, and then just put it 0. And then you basically start from the same point and then slowly decrease your line, pass it through this, and then increase and then increase it slowly like that. Alright, so that would be the net electric field strength line.
Sir, can't
Yes.
we take it at like 10 or 11? Because it looks more closer or accurate.
10 or 11. 10 is not. 10 is like 1 and 1.5, and on the top there's 3.
So it's 4.5. Here it's 2 and 2 it's 4. Okay.
So I took 2 and 2 like that. So that's
Okay,
when it's gonna get cancelled out. That's what I'm saying.
Sir, they said sketch from 4 micrometers.
Sorry?
They said in the question sketch from 4 micrometers. So where did we do that?
From then, if they say 4, then you just
Then we
do,
can start from 4, right?
yeah, you can like this. The line will be then. And till what? 14? They
Till
said?
16.
Okay.
16 micrometers.
Till 16 it will like be a little bit not touching actually. There's still value there, so it will be somewhere here like that. Like that. You understand?
Okay, so we don't touch the graph at 4.
No, because you can only touch the graph when the graph is really low. You see?
Right.
It was like quite significant value here, so I did not touch it then. Okay, like that.
Okay.
So, but the thing is that make sure that your line should be like smooth, and that's all you needed to do. Okay, so this graph is the same thing that we've done, so I'm gonna give this as homework, and I believe you guys can do this. This is very simple. This graph is also the same, so homework. So this is just practicing of all the graphs we've drawn. Everything else is quite similar question. Let me see, what is this? But I think I'm gonna solve this question. The rest of them you can do. Anyway, so in this question it says the positively charged particle in B2. B2, where is B2? I don't know. B2. B2 says without any calculation, describe the force acting positively charged particles placed at point P. for the values of x 0 to 10 centimeter. So from 0, obviously the force will be maximum because gradient is like highest, and till 10, here the force will be 0, and then here the force will be in the opposite direction, right? Is it clear? I think, yeah. Anyway, so that would mean that basically this is what we explain. They say the charge and mass is given by this equation, right? So they say initially the particle is at rest on the surface where x is equal to 0. Then it moves freely along the line joining the center of sphere until it reaches the surface of sphere B. Mark with letter M the point where the charged particle has its maximum speed. Obviously, the maximum speed, because you know work done is given by change in potential times charge, and wherever the change in potential will be highest, so when it is highest, then you will have maximum work done, and maximum work done would mean that you will have then maximum kinetic energy, right? So if you look at this, it basically started from this point, and which is right here, and it ended like the lowest point on this graph is this line, which is somewhere here basically. So this would mean this is the biggest change in potential that you're going to see. So it means this is the point P. This at point P, right? Mark M. Okay, so this is the point M where it will have maximum energy because that's the most work done on it. Is it clear? All right, then it's gonna say use to determine the potential difference between spheres. Use figure 5.2 to determine the potential difference. It's pretty easy. You know that this is where it reached the surface, right? So what is this value? Can you please tell me?
$570.
570. Okay, and what is this value?
230.
230. So the difference is 570 minus 230. What you get? 320. So just write the answer. 340. Okay, 340 volts should be the answer. And then it says use your answer in part 1 to calculate the speed of particle as it reaches the surface of sphere B. So we have the change in potential, right? And which is 340, which is great. And then you got like you know that work done is change in potential times charge. So 340. Do we have the charge for this? We don't have the charge, right? That's not fair. That's not
Oh,
fair.
wait.
But
That equation.
it's all right. Sorry?
That equation on below.
But then we do not have the mass as well. So I'm gonna play a trick here. So what I'm gonna say is this is the work done in causing it to gain speed. Do you guys agree? So that should be like equal to kinetic energy, no? Which means that then half mv square should be equals to 340 times the charge, and then 2 will multiply there, and v square will be equal to 340 times the charge times 2 divided by the mass and taken under root. Do you guys understand this? Then what you're going to do is you're going to see that this part of the graph basically shows that this is this value that they've given, which means I'm going to have root of 340 multiplied by 4.8 times 10 raised to the power 7 and then 2. What you get? Yes.
1.8 times 10 raised to 5.
4.8?
1.8 times 10 raised to power 5.
Okay, who did not understand this? Please let me know. This was a bit tricky. Okay. All right, Tanjim and both Ahmeds and Mokshit, you guys understand everything? Okay.
Here's the first part
Yeah.
where you're marking the letter
First part, what? Anusha?
where you're marking the letter M. I don't understand that part.
This one?
No, the first part of the question, CI.
See, where I'm marking that. Oh, okay. I'm gonna tell you that. So what I'm saying is, you need to understand that work done is going into kinetic energy. You agree, Anusha? And work done, the kinetic energy, work done is basically charge times change in potential, right? You agree?
Yes.
So, with respect to this, can we say the change in potential is proportional to the kinetic energy? Because charge is same in this. What do you say?
Yes.
So it means the greater the change is, the greater the kinetic energy is going to be.
Yeah.
It means that if you look at the graph, where is the greatest change shown? From this point to this point. So the change will be like this. Is there any other point that shows the any other larger change? Do you see that?
Yeah.
So it means if the greatest change in potential was here, which means this would have converted into kinetic energy. So at this point, it will have the maximum kinetic energy.
Isn't it supposed to be where the voltage is the max?
No, because the formula states work done has to be the change in potential times charge. So we got to find the change. We're not finding the maximum voltage.
Okay.
You get my point? In fact, at maximum voltages, this is just for your understanding. I'm going to write it down. So at this point, the velocity will be 0. Because we also need to follow the law of conservation of energy, which states that potential energy goes to kinetic energy, right? So how is the mass getting, like, how is this charge or particle is getting speed? Because potential is decreasing, right? So potential energy is decreasing and you're gaining kinetic energy instead. That causes law of conservation of energy to conserve. Do you understand?
Yes, sir, I got it.
All right, good. So the next question is the same. You're gonna do that yourself. And this question again, it's the same. Go do. So this time I've like put many questions just to, and if you don't understand something, do let me know, okay, so that I can explain it later as well. Anyway, so then we also would be required to write the differences between and similarities between the both fields. First of all, we're going to talk about the type. So gravitational field is an attractive type, and electric field is both attractive and repulsive. So it depends. Then we're going to talk about the law. So gravitational field follows Newton's law of gravitation. Let's write that. Let's write the right thing. And this follows the Coulomb's law. Then we should talk about the force. In gravitational, force is given by G(m)m over r square. In this one, it is kq q over r square, or we can write 1 upon 4 pi epsilon times qq over r square, like that. Then we're going to talk about the work done. In this one, it was basically work done was given by, we could say GMM over R, and this one it is KQQ over R. And in this one, then we can write the potential as well. The potential, gravitational potential symbol was like this. It was minus GM over R. In this, the potential is work done over charge, or we could just simply say, in this, work done over mass, and that work done over charge. And we can simply say plus minus KQ over R. Plus minus because it really depends on the charge, if it's a positive charge or negative charge. And then we got field strength. So in field strength, this was G, which is force per unit mass, or GMM over R, GM over R square. And in this one, the field strength was given by E, which is force per unit charge, or KQ over R square, right? And finally, in this one, direction of field, what that determines, right? So direction of field is determined by path taken by a unit stationary mass. All right, and in this one, it is the path taken by unit positive charge that is stationary. All right, so that is what you should remember. Okay, so both of them have like quite basic similarities and quite many differences, but generally the whole feel of this is the same because the formulas correspond to each other with respect to inverse square law and everything else. So you can remember that. So you can take a screenshot or you can write it down, please, and then we're going to go forward. Okay, now should I go forward now? Okay, now we're going to go to a question like this, where it says, by reference to electric field line, explain for points outside an isolated spherical conductor, the charge in sphere may be considered to act as a point charge at its center. All right, what do you guys say about it? I already told you this already. Yes, please tell me. Why do you think that for a simple isolated sphere, when we were drawing the field, why do you think it can be considered to be a point charge? Yes, please. That is not fair. You guys should have.
The lines appear to come from the center. They radiate.
Yeah. So for 2 marks, if I were you, I would write that lines, I told you, are always perpendicular to surface, and they appear, writing appear is something very important, appear to come from the center. So you should write that and it would give you 2 marks. All right. Now, in this sort of question, it says 2 isolated spheres, 2 isolated protons separated by vacuum by a distance x. Okay. Calculate the ratio of electric force between 2 protons. So they're talking about one proton and another proton, and their distance is x. So electric force would be KQQ over R square, and then we're dividing it by the gravitational force, which is going to be GMM over R square. Do you guys understand this? Now, if you notice, both distances are same, so this and this will cancel out, leaving you with KQQ over GMM. Now we need to find the ratio. So K will be 8.99 times 10 raised to the power 9, and Q will be 1.6 times 10 raised to the minus 19, and then 1.6 times 10 raised to the minus 19. Divided by G is given by 6.67 times 10 raised to the minus 11. The mass, like I've remembered this by doing so many questions, you can also remember this by doing so many questions. It will save a lot of time for you. And the mass of proton is 1U, which is 1.66 times 10 raised to the minus 27, and 1.66 times 10 raised to the minus 27. All right, what you get? .66. Yes. Please give me an answer. That's not fair.
1.2 times 10 raised to 36.
So it's going to be 1.2 times 10 raised to the power 36. So it means, basically what it means is, it means
So
that,
it's 1.25.
Sir, I got it as 1.3 times 10 to the power of 36.
are you sure about that?
So if it's 1.25, won't it round off to 1.3?
It
Yeah, it
should.
should, because that's what's on my calculator too.
Yes, 1.3 into 10.
1.3.
Okay, we are gonna write 1.25. Okay, happy? It doesn't matter.
So why not 1.3? Because it's 1.25.
You can write it. You can write 1.3 as well. That's fine. Not a big
So
deal.
1.3 into 10 to the power 36.
Yeah. So what basically this value is telling you is that the electric field, the force due to electric field is 1.3 times 10 raised to the 36 times greater than force of gravitational field. Do you understand that?
So sir, can't we just write like the ratio is because as G is less than 1.3 into 10 to the power 36.
No, in this part you just need to give the ratio. Okay.
So ratio is typically with the semicolon, right? Like, so that's
No,
how-
no, 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 no. In physics, it automatically means that you basically, like these two you've divided, so this is the ratio. Do you understand? So you don't have to do
Yes.
that. Yeah. You don't have to write 1.3 times 10 raised to the 36 ratio 1. Don't do that, okay? All right.
Okay.
Now, it says in the next question, by reference to answer says why gravitational forces are not considered when calculating the force between charges. So, what do you
So
guys
they're
say?
negligible, right?
Yeah.
Because 1.3, because the ratio is crazy
Yeah.
big.
The difference between the magnitude is very large. That makes force of gravity insignificant. All right. So that's what I'm going to write if I was giving the exam. All right. Is it clear, everyone? Okay. Now we are gonna go back to yeah. So we're gonna go to the next page. This particular question.
Sir, could you show that question again?
Yes, please. You can have a look.
Sir, that makes what insignificant?
It makes the gravitational force feel
Oh.
insignificant, right? Because
Okay.
10 raised to power 36 is I don't know what. More than a trillion, I think. Probably. I don't know. Alright, is it clear?
Yes, sir, thank you.
Okay. Alright. when I'm solving something, please do keep checking the mark scheme as well, because sometimes I can make a mistake as well, and you guys should correct me. Anyway, going forward. So then it says state one similarity and one difference between electric field strength. Can you please tell me one similarity? There got to be some similarity. Hello, there should be. They both follow inverse square law. Forgotten already? All right. Then the next thing is that and the difference is you can write the law, you can write the formula, you can write any difference that I put in the table, and that would score you some marks. All right, is it clear, everyone? Okay, then we're gonna go towards you're gonna go towards this one. It says a positive charge q is positioned at a fixed point x, and blah 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 blah, and says calculate the charge on q. So they both have the same charge, right? They say the electric field strength at A is this much, and obviously this is talking about the electric field strength that is due to this and this. Do you guys understand this? Now think carefully here. What you see is, because this is a positive charge, it means that the electric field due to x is going to go away like this, and obviously the electric field strength of y is going to be like this, because charges electric field go like this. Do you understand that? So at this point, what you're going to do is we are going to find the electric field strength of x first. So with respect to x, we can say that it is basically k times q at x divided by r squared. So k is 8.99 times 10 raised to power 9. The charge is just q, and then the distance is 2.5 centimeter, which makes it, I think, 0.025 whole square. All right, everybody understands this? Then for EY, we're going to do the same, KQY over R squared. So this time K is the same, charge is Q, and then you got a distance of from here till this point, and that would be 10 minus 2.5, which is, I think, 7.5. So 0.75. 0.075, yeah, 0.75 whole square. Now basically what these two are not equal, so the change in gravitational field strength at that point is given as 4.1 times 10 raised to power, or let me write it here, sorry, 4.1 times 10 raised to power minus 5. And what we're looking at EX minus EY. So we're going to write 8.99 times 10 raised to power 9 times charge divided by 0.025 whole square minus 8.99 times 10 raised to power 9 times charge divided by 0.075 whole square. All right. Now the question is, you solve this and find Q, please.
Could you simplify it further? What do we do with the negative?
Do nothing. You just find, you need to find this value using your calculator and this value using your calculator, and then subtract these two. In terms of Q, you'll get it.
Okay, sir.
Yeah. that's pretty good. Okay. So and the answer is, what do you guys say? Interesting. Slow people.
So it's 3.2 times 10 raised to minus 18.
Oh, okay. 3.2 times 10 is to negative 18. So that should be the charge. If it is wrong, blame Gatika. All right. Is it clear, everyone? So I hope you guys understand this question. This was a bit tricky one. Apart from this, I just want to tell you that this is very similar from the previous one. So you can draw the graph yourself now. And then obviously,
Sir, the answer is 3.2 times 10 to the power of negative 18, right?
yes, that's what Gatika has said, not me. And then this question is very similar. So you're gonna basically do this yourself, and it is the same as the one we did earlier. And now we're gonna move to the last part, which is, I think this is not the last part. I think there has to be, yeah, there is, yeah, we have to, do that later as well. All right, so I'm gonna draw the graphs today, and then tomorrow we can just finish this chapter. So what happens is that you guys need to understand, like I said, the potential when you're looking at solid conducting spheres, which are metals, because the charges can freely move. So basically the charges gather around the whole thing like this, right? So within that solid sphere, you just need to remember that the potential stays constant. So it stays like constant, and then it decreases with respect to V is proportional to 1 upon R, like that, right? So when you've drawn this, you can draw the other graph as well. So for that one, all you need to do is you need to take the gradient, right? So here in the first section, if you look at this part, you see the gradient is 0, and the reason why gradient is 0, it's a flat line, which means that this graph should start from 0 till you reach the surface, and then it's going to jump up, and from here it is going to make a very sharp curve. Why? Because electric field strength is proportional to 1 upon R square, like that. All right, so it should be a sharper curve than the potential one. All right, so this part comes a lot in your exam. So if you've drawn this, we'd like to go forward. All right, so then let's go forward and let's talk about the question here. So in this one, it says what is meant by electric field. You got to do that yourself, homework. But then this one, it says that there is basically a solid metal isolated sphere, radius r, charge on the sphere is q, and electric field strength is z. So you got to draw the lines from 0 to 3r. Now these sort of graphs, you need to understand till r, which is the radius, the line should be absolutely 0, like that. And then it would jump to E at the surface, like here. Okay, let me just make a nicer line. It should jump to E, like this. And from this point onwards, oh my goodness. From this point onwards, you're going to decrease it by a square. So what happens is 2r would mean that electric field strength is proportional to 1 upon r square. So 2r would mean that electric field strength will be now at 2r square, it will be a quarter, right? So a quarter would mean 0.25. So at 2r you're going to write 0.25, and 3r it is going to be 1 upon 9, right? What would that be?
So 0.11.
0.11. So if this is like 0. I know what that is. I think it should be 0.125, right? It should be somewhere here, and that would be here. So you just then make a smooth line to cover that up like that. Is it clear, everyone? Just like this. Anyway, the rest of the question, it says that the sphere has a radius of this much, and the electrical breakdown occurs when the electric field strength at the surface of the sphere exceeds this. Determine the maximum charge that can be stored on the sphere before the electric before the electric breakdown occurs. Okay, so this sort of question, I just want to tell you, this is the sphere, okay, and the radius of this sphere is given by 0.26 meters, and the maximum electric field strength is this one, right? So at the surface, right, we're going to say electric field strength is kq over r square, right? So the maximum is 2.0 times 10 raised to the power 6, and then it will be 8.99 times 10 raised to the power 9. We want to find the charge, and the distance is going to be 0.26 whole square. Can you please find that?
(1.5 times 10 raised to negative 5).
1.5 times 10 raised to a negative 5 coulombs. Okay, well, it doesn't seem okay to me, this answer. I don't know, it could be the same, I don't know, but
Oh, sir, I'm getting 1.5 into 10 to the power of 13.
that's not fair.
Sir, I got Karthika's answer 1.5 times 10 to the power negative 5.
Then Mokshit, you're doing something wrong. You are doing something wrong,
Let me
and you're doing the same. Basically, you're using the calculator wrongly, I believe that.
It might be, yes, sir.
Yeah, so if two people are getting the same answer, then
See,
that's
I
fine.
usually we have to take 2.0 into 10 to the power of 6 into 0.26 square
Yeah,
divided by 8.99 into 10 to the 9, right?
yes, but then you have to put you're doing this. So you have to put a bracket here when you put it into the calculator. Then you get the
Okay.
All right. Okay. So I believe you guys understand something out of it, and then I will see you guys tomorrow. Have a nice day.